we'll be starting the next section of our workshop now. So moving away from the built environments into the natural environments, we'll have our keynote talk given by Professor Abigail Bodner. So Abigail just recently joined MIT here, jointly appointed between the Department of Earth, Atmosphere, and Planetary Sciences, as well as EECS through one of the joint Schwarzman College of Computing hires. Previously, she was a Simon Society Junior Fellow working at the Cron Institute of Mathematical Sciences at NYU. Abigail completed her PhD from the Department of Earth, Environment, and Planetary Sciences at Brown. She holds master's degrees in applied math from Brown, as well as atmospheric sciences from Tel Aviv University. Dr. Bodner's research spans climate, physical oceanography, geophysical fluid dynamics, and turbulence. She investigates multi-scale turbulent interactions in the upper ocean using a combination of theory, numerical models, and data-driven methods. And Dr. Bodner is also the creator and co-founder of Climate Match Academy, an international volunteer-driven organization teaching computational tools for climate science. So join me in giving Abigail a warm welcome.
All right. Hi, everyone. Thanks for inviting me to speak today. I feel like this is going to be a very sharp transition from the first kind of theme of the session, but my work kind of is more in the climate field, but more on trying to understand the physical climate and what we still don't know and what we still need to discover. So as kind of I go through the talk, a lot of the focus is on the more theoretical work I've done in the past and numerical machine learning stuff, but I'll try to draw connections between where observations could be useful, which is where I think the best kind of interaction and collaboration with people that are interested in robotics and how you can utilize robots in order to measure the physical world. So let's see how this goes. So as kind of, I hope many of you know, or probably the motivation of you to be here today is because you appreciate that the climate system is very complicated. We have a whole lot of processes. Sorry, I'm going to take this off. We have a whole lot of processes that interact over a very wide range of spatial and temporal scales. So that covers the atmosphere, the ocean, land, biology, sea ice, anthropogenic forcing, which we heard a lot about in the previous sessions. And all of this is, again, is extremely nonlinear, and it's very hard to quantify. We try to do so the best we can in what we call general circulation models, sometimes abbreviated as climate models. In order to do that, we try to capture as many processes that we think are most physically relevant for these models. But naturally, we're limited by the size of the domain. We're limited by grid spacing, time stepping. So anything that's too small, too fast, or too complex goes unresolved in these models. Unfortunately, sometimes the smallest scales are the most complicated ones, also have very large impacts on the climate system as a whole. And my work involves trying to understand the ocean's role in this, and in particular, the upper ocean, where we have a lot of sensitivity in climate models. So you may have seen plots like this before. So this is kind of projections of global surface temperatures over the next century. And what I want to note here is that we can see different scenarios. So there's like business as usual, best case scenario, worst case scenario. And what we're seeing here is on kind of the left side of this figure, that's observations as well as models that are making kind of past predictions. And then the different colors on the right kind of part of the figure are projections into the future. And what you'll notice is that there's a wide spread in what models think will happen in the future. And one of the main reasons we have such disagreement between models is because what's happening at the smallest scales that we can't resolve. So the large scales, we kind of understand the dynamics. We are able to code up the equations into the model, but at the very small scales, we try to estimate it with all sorts of parameterizations, which I'll be talking about today. So in particular, the ocean mix layer, which is kind of the upper layer of the ocean, this is kind of the focus of my work, and also where there's a lot of sensitivity in climate models. There's a lot of mixing and turbulence, in the upper ocean. So if anyone has been to the beach or even just, hanging out outside, we experience winds, we experience we don't experience waves on land, but there are waves in the ocean. There's precipitation and heating and cooling, and all of this is leading to a lot of mixing near the ocean surface. But how well mixed that is, how much turbulence really affects how heat is transmitted between the atmosphere and the ocean. And if we think about climate change and what we really care about, we think about carbon, we think about heat, we think about energy. And all of this is really determined by what's happening in the upper ocean. Unfortunately, these are very small in scale, and I'll get into that in a little bit. But what that really means is we can't resolve them in climate models. So on one hand, we have processes that are very complicated, but also very small. We know they affect the climate, but we can't resolve them. So there's a lot of work by the community to try to understand the physics, understand how to quantify the physics, and then put that in climate models. Also, please feel free to interrupt at any point if you have questions. All right, so just to drive this point a little further, what we're seeing here is the North Atlantic. It's very pixelized. This is a model, which is kind of a standard ocean model. It's 100 by 100 kilometer grid. So I got my PhD at Brown, and we'd like to joke that this is a non-Rhode Island resolving simulation. So all of Rhode Island is kind of captured in one pixel here. And what we're seeing here is sea surface temperature. So I'm going to hit play. So you can see the warm and cold temperature are kind of moving around, being advected, but we don't see a lot of features that we know exist in the upper ocean. So for example, we don't even see the Gulf Stream, which is a very large scale feature. And everything that falls below these 100 by 100 kilometer grids needs to be accounted for somehow. So we account for them by some parameter or parameterization. This is what's thought of as the next generation of ocean models. It's a 10 kilometer resolution model. So kind of the standard models that get used in the IPCC report, such as the figure we saw in the beginning that project temperature into 100 years, those are kind of the upper left models. So that's the standard model that we get used. And then we're slowly transitioning into the community into these 10 kilometer resolution models. But still, there's a lot of work that needs to get done into how do we really capture these high resolution processes. So we're starting to see more features that we know exist in the upper ocean. We can see the Gulf Stream. We can see these vortices, which are known as eddies. They're similar to ocean storms. This is already a Rhode Island resolving simulation. If we were to zoom in even further, this is what's known as a regional ocean model. It now has a 1.5 kilometer resolution. This metric is known as vorticity, which is a measure of the rotation in the flow. And I hope you appreciate there's a lot more complexity now in the flow. You can see large and small vortices. You can see kind of energy that looks like it's being moved around from large and small scales, and we see the Gulf Stream is more pronounced. If we were to zoom in even further, this is the Chesapeake Bay, a 500-meter resolution model. There's a lot more fine-scale features going on, and you can keep doing this. You can keep zooming in further and further until you get down to the molecular scale. So the processes I'm interested in, and the ones that we have a lot of sensitivity to in climate models, are the ones that are happening at the very smallest scale. So only now we are starting to resolve the processes that we know in the upper ocean kind of determine atmosphere-ocean interactions and climate sensitivity as a whole. And the question to be asked really is, well, what is the important physics that we need to capture in those very coarse models? What's missing? What is the quantification that needs to be done of the essential physics that we can then use in the low resolution models? So unfortunately, because these are very small scale, because they're also very fast varying, we tend to be very limited by how we can measure them in the real world. And this is, I think, where also this workshop has a lot of potential in my field, is that we're really lacking the ability to look at these very, very small scales. So in the ocean, there are a lot of different kinds of ways that we can measure. It's a little more difficult and involved in the atmosphere. Because in the atmosphere, we've also been taking measurements for a lot longer. But a satellite that's floating around space can essentially measure kind of most of the atmosphere. In the ocean, that's not the case. We can measure the surface of the ocean using satellites, but anything that happens below the surface is an enigma, right? We have to send in devices, and they're called in situ measurements. And there are a variety of different ways that we can do that. So does my cursor work? Yeah. So these are known as moorings or buoys. You may have seen them if you went out into the bay at some point. They stay fixed in space, and they have an array that goes down into the interior, and those can measure velocity, they can measure temperature, density, salinity. Sometimes they also have all sorts of biological metrics attached to them, and you can get a lot of information within that fixed point. So all you're measuring is water that's moving across that point. You then have these floating devices. They're known as drifters. It's basically like ocean drones, and they are floating with the water. So what they do is they go up and down, and when they go back up to the surface, they transmit information of what they measured. And they capture kind of columns of information of the water, and that can give us measurements of, again, temperature and salt and all sorts of like oxygen metrics and stuff like that. And then there are ships, or there are kind of dedicated campaigns that go out to a certain region, and they try to kind of travel along a certain intersection, taking these same type of measurements. Some people even take advantage of like sea mammals. So there's a really cool campaign in the Southern Ocean where they attach like radars to seals, and those seals kind of dive up and down, and you can understand the dynamics that way. And that's pretty much it. You know, like we really have these like samples in space and time of what's going on in the ocean interior. And the figure on the right is showing us kind of the density, the global density of all of these different types of measurements. The world is really big, right? So between every 2 points, we could have hundreds of kilometers. So referencing back to the very small scales that we know are important for climate, we are not really able to understand them in the distribution that we need globally in order to really understand what's happening to the climate system and how these small scales affect it. So we still have this gap in what we can measure, what we know is important, and how can we model it for the future. So a little more about kind of the scales that I'm after and why they're so interesting. So these are known as sub-mesoscale flows. I'll try not to use that jargon a lot here, but they're about kind of 1 kilometer in scale. Some tend to be smaller, some tend to be larger. And what we're seeing here is chlorophyll concentration. So that's a useful metric to understand biogeochemistry. A lot of fish tend to feed off of nutrients in the ocean. So this can kind of give us an indicator for where there's a lot of interesting biology, and also where this like ocean atmosphere exchange is happening. There are these different features. So you can see down here, this is a filament. It kind of looks like a hair or a streak. These are known as fronts. It's like a sharp interface between 2 types of fluid. I'll get more into the details on this in a little bit. And then there are all sorts of instabilities that can form. So these are like vortices or eddies. I lost my cursor. Here it is, which form along these fronts and filaments. And this is also kind of a metric for what's really happening in the ocean and what's causing this turbulence. So here are some pretty pictures of fronts. So fronts have been an enigma for the community for decades because on the one hand, they're very coherent. So you can see them. You can actually, like, next time you're on an airplane and you're landing in Boston, there are some really cool fronts that you can look at from as you're landing. And it usually happens when you have this, like, near the coast, you have fresh water that's very warm, that's coming into like the deeper, denser ocean water, and you get these very sharp interfaces that form. So this upper left photo is taken in the Gulf of Mexico, where you have the Mississippi River that's pouring into the Gulf water. You get these really nice features. So you can see for scale on the left, that front is very narrow. It's probably a couple meters wide compared to the ship. But on the top right, that's from the Gulf of Mexico oil spill about a little over 10 years ago. And it's the same location, right? But notice, just for scale, what we're seeing here is a front that's transporting oil on its interface. And that's a ship for metrics. So within the same region, we can have very widely different features, despite them kind of being in similar dynamics. On the bottom left is sea ice in the Arctic. So we can see a front is, again, transporting sea ice at its interface. It's being squeezed by larger scale vortices. And if you were to slice through a front and look at the interior, you would see that there's a lot of nutrients that tend to hang out along these fronts, like we saw in that photo in the beginning. And that, again, is an important feature for like fisheries and biology, because we can really understand, like if we're thinking about how climate is changing, if we see certain different interactions of fronts, for example, we can also try to understand how that's affecting the fish. So despite the fact that we can look at these, we can take pictures of them, how we understand their dynamics has been really convoluted. And then how we can account for this complex physics in climate models has even been more difficult. So that's kind of going to be the focus of this first part of my talk. I'm not going to get into the math, but I will just say that due to the lack of observations, a lot of the work has gone into trying to theoretically understand how these are working, and how you can also understand them given all the other craziness that goes on in the ocean mixed layer. So what happens when we have winds and we have waves and we have like cooling at the surface. So some of my work was involved in trying to come up with a new scaling law to understand how these fronts interact, both in like a kind of a quote simplified theory, but also using very high resolution numerical simulations. I will not get into this, but if anyone is interested, I'd be very happy to discuss. So it turns out that even like changing the small parameter of how wide these fronts are can actually have a really big impact on climate. So this is just kind of example of like, because we don't have observations, we have come up with a new scaling law, but how the scaling law can impact climate is very large. So remember that we said that these small scale processes, this turbulence really affects most the mixed layer in the ocean, and how much turbulence is affecting the ocean and the atmosphere interaction. So going back into different types of models, I was able to look and compare and see how really, what's the impact on the climate. And turns out that it does have a large impact. Again, I'm not going to get into this too much, but even a very small parameter can impact, for example, what's happening in the Arctic, what's happening in the Southern Ocean, in the equatorial Pacific, and all of these have very important climatic effects. So that's kind of the first part, which is related more to like the physics-based parameterization. So how can we use physics in order to understand the ocean flows and then improve climate models? But what I want to point out, and this is where I'm transitioning more to like data-driven approaches, is that even though we came up with this new scaling, this new theory, we can still see kind of from these I'm sorry, it looks really pixelized here, but we can see that these two kind of plots don't really match up. So on the left, on the top left plot, that's like what we would think of as like true data from a very high resolution simulation. And the one on the right is like what the physics says it should be. And just by kind of eyeballing it, you can see that there's a lot of information still missing. So we're missing in particular these like negative patches that just by construction we're not able to get with the like purely theory driven approach. And there's also some large scale features that are missing. So the question is, can we do better with data? Is there something that we can use, like apply machine learning for example, in order to capture the missing physics that we're still not able to get from theory? All right, so this is kind of one of the highest resolution ocean models that are out there. It's about 1 to 2 kilometers in scale. So compare those to those low resolution models we saw at the beginning. It's about 50 times higher resolution, right? And what we're seeing here is 1 year of simulation. Okay, I'm sorry, it looks much nicer on my screen. Hopefully you can appreciate it's very high resolution. But what we're seeing here is we're seeing some very fast frequencies. If you notice, that's the atmospheric forcing at the surface, and then they're kind of lower oceanic timescales that are moving around. What we're seeing here is essentially fronts all around the world. So this is measuring like how intense those gradients are, which is motivation for where we think these processes are important. And those blue squares are is the data essentially I've used to train the network that we'll be talking about in a little bit. So hopefully you can notice that there are certain patches around the world which have kind of stronger yellow parts in it, and that means that there are stronger fronts there, whereas other parts are more quiescent, so they're darker patches, and that means that there's not as much going on. And the idea was, like, can we train a network to predict the turbulence within those regions based on a very wide range of dynamics that exist around the world? So we tried to account for kind of different places with different dynamics and see if we can generalize this approach. Oops. Okay, so the tricky part here really is well, what's important, and what is really kind of the learning method we want to do. It's not like, for me at least, coming from a very theoretical background, it wasn't obvious how we want to structure this problem, and what do we really want to learn, and what do we need in order to learn and train the network. So what I ended up doing is, from each one of those regions, trying to think about really what are the most physically relevant variables that we need in order to predict this problem. And on the left, those are a whole bunch of different physical variables that are related to the small scale turbulence, which were computed from this high resolution simulation. So from each one of these regions, we computed different variables, such as, for example, the flow field related to the heat flux, related to how deep the mixing is. And all of those were used as part of the input features of the neural network. And then in an attempt to say, can we predict the turbulence that's below the resolution? And again, the goal is, if we can improve the predictions of these small scales, then we can go back into climate models, implement it, and see if we're able to kind of reduce sensitivity in climate models. So it was, at the end, it ended up being a pretty simple problem. We have inputs and then a trained neural network to predict these small scale features below the grid. But there was a lot that went into pre-processing the data. It's huge. It's like petabytes of data that's stored in some NASA computer. And most of my postdoc was involved in trying to like actually get the data, pre-process it, make the computer not crash, and get it to a point where you could train. So this is all to say that the data really does matter, and how you approach the learning problem also requires probably more thought than training the actual network. So spoiler alert, it went really well. So what we're seeing on the bottom left is the quote truth from the simulation. This is unseen data by the network. And on the right, this is the prediction of the neural network of that same region. And kind of just visually, we can see it works pretty nicely. We can see that we're getting a lot of the similar features. On the top right, we're seeing more of like a statistical observation. So the upper panels are the theoretical prediction, and the bottom panels are the CNN predictions. So hopefully you can appreciate that the CNN is really following this like one-to-one line, compared with like kind of the more just diffused theoretical prediction, which means that we're staying a lot more closer to the kind of true data than we are in the theoretical prediction. I was also really interested to see, so there's a lot of seasonality that is associated with these small scale turbulence. So you can imagine when we have stronger winds, stronger waves, stronger like cooling at the surface, such as in winter times, we would tend to get a lot more stronger turbulence. And that's where we really struggle with measurements. That's where we struggle also with theoretical approximations. So what's plotted over here on the top right is a seasonality of 1 year of unseen data. So this is telling us how strong this turbulence is in a certain region over the course of a year. This is all unseen data by the neural network. So in blue is the true data, in green is the theoretical approximation, and then in orange is the neural network prediction. And what we can see is that the neural network is able to stay really close to the true data, which means that it's really capturing the intensity of this turbulence in the mixed layer, and it's probably better capturing also how the ocean and atmosphere, for example, interact. In particular, also where in the winter months, where we expect to get these stronger winds and much cooler surfaces. And this actually ended up being true for all the different regions that we looked at. So even though what we see is there's a lot of really different dynamics, so no one region is alike to another, and that's because we have very different behavior around the world, right? We have different wind patterns, we have different temperature patterns, and all of those are affecting the ocean circulation in different ways. But we can see that the neural network is really able to somehow learn the relationship between what's happening and what the small scale turbulence should be. So after, check that worked, one thing that was interesting was, why is it so good? Like, it's also kind of not really a surprise that the neural network will get it right. But at least once kind of the problem is structured properly. But one of the questions I was after is like, well, what's missing from the theory? I thought the theory was good. I worked on it for a while, but it turns out not as good as I thought. So what are we really missing? So then kind of I deployed two explainability methods in order to try to understand really, well, what is the network learning that we don't know yet? So there are two main approaches, and this is probably something that some of you have thought of already. But the first one on the top is taking all of the input features and then removing one at a time. So if a feature is important, it should reduce the skill significantly in the neural network. And that will tell us that the neural network needs that in order to make that prediction. And the second one is to look at this local sensitivity, which means that we're tracking essentially gradients across the weights. And that will tell us that in a certain location, if we backtrack, that input will be very important locally to that output prediction. And this gives us two kind of different views of the same problem. So the first method of removing an input is more of like a non-local impact because the network needs the entire domain to make that prediction. Whereas the second experiment or set of experiments will tell us about what is locally important. And it turns out that the features that come out are different. So in the first experiment where we removed an input feature, it showed us that by far across all kind of the different resolutions I checked, the strain field is the most important. So strain is associated with large scale ocean flows, which is telling us, remember that sea ice picture where we saw the large scales that's straining those fronts? That's really associated with how the large scale is affecting these really small scale turbulence. Whereas locally, we're finding that how deep the mixed layer is, so how much mixing is already in the upper ocean, is affecting it locally. And what we're seeing is that these processes, this turbulence is really sandwiched between the very large scale ocean flows and what we really can't resolve, the small scales. And what we need is probably different approaches beyond the framework of this work in order to push forward and improve the predictions. So it's kind of like the same story that's always been told, but this really highlights kind of the two ways or two different features that we need in order to improve predictions. So currently at MIT, so this is all kind of previous work, and I just started a couple of months ago, starting to build my work group and work on new projects. And what I really would like to do is combine several different frameworks or different types of data sets in order to push forward on these ideas and get into really the nitty-gritty of how we can improve climate models. So I don't know if anyone here has heard of Oceananigans. It's has a great name. It's a model that's developed here at MIT. It's Julia-based, so it can run on GPUs, compared with pretty much all other climate models which run on CPUs. They're also built in Fortran. I know. And they're really hard to work with. They're really slow and they're heavy. Whereas this new GPU-based model can really push the limits in terms of high resolution modeling, which is what we need for these very complex and small scales. So this is kind of a nice heat map of the flow, but we're working on a massive new simulation, which is super high resolution, but very large domain, which will allow us to look at kind of the interaction across all the very wide range of scales. There's also a new satellite that was launched almost last year at this point, which is known as SWOT. I don't know if anyone here has heard of it, but it's going to be measuring the ocean surface as the highest resolution that we've ever had before. Which means that we're finally going to have an opportunity to test some of these theories and also extend some of the work, for example, that I have done using the simulation data, but on real observations. The problem is, though, is that satellites only give us the ocean surface. As we mentioned, a lot of the important information is hidden in the interior. So I'm really looking forward also to getting into in situ measurements and then think about how we can apply, for example, machine learning and data approaches in order to combine all of these three different approaches and see how we can utilize different information from different methods in order to get a more complete picture of ocean dynamics. So we mentioned Climate Match earlier, and I just wanted to say it's a really wonderful course if you're interested in learning about data tools for climate science. Unfortunately, the registration for this year is already closed, but if you have experience in the field, it could be anything related to climate and in the intersection of data, You're welcome to apply to be a mentor for students who are just getting into this field. So the applications for mentors are still open, or if you wanted to take the course, you could look out for it next year. And I don't know how early or late I am, but good. Okay, so with that, I'll conclude. So I discussed kind of more the physical side of climate and how I work on upper ocean dynamics in order to try to understand the physics and also try to improve climate models for future projections. We talked about a physics approach and a data-driven approach, and also kind of looking into the future. I'm really keen on thinking about how we can use new observations and new open source modeling tools in order to push these ideas forward. And hopefully in the context of robotics, we can see some intersections related to the data that we gather and how well we gather it, and then how we can apply stuff like machine learning in order to improve predictions.
Thank you for that great talk, Abigail. I want to start off, maybe for those aren't familiar with some mesoscale processes and everything. You showed us a map and with some of these boxes where you're sort of interested in these processes. Are there, I guess, general regions where these order 1 kilometer scales are really important that we really want to target in the ocean geographically?
Yeah, so so actually those boxes were really motivated by places that we know. We've had observational campaigns that have gone out and tried to measure some of these flows. So in particular, like the North Atlantic has been a hotspot that people have been looking at, also because it's proximity to the Arctic, and that we know that kind of if patterns change around there, or if like heat changes around there, then that will have implications for the climate system. California coast has really been a big place for measurements. The Southern Ocean, where we know that there's a lot of carbon uptake, for example, by the ocean, and submesoscales, or these, I try not to use that term, are playing a big role also in kind of transferring carbon between the atmosphere and the ocean. So it's usually in places where we see a lot of small scale activity, a lot of times near the coastlines, but also where we have very strong currents, such as the Gulf Stream or the Mauricio Current or Southern Ocean, for example.
Yeah. And I guess building off of that, not only are these regions perhaps important and these properties important for climate, but could you touch on, you briefly mentioned their impacts on biology and sort of the ecosystems. Do you want to touch on sort of maybe the impacts specifically that they might have on fisheries or sort of communities that, people here might be interested in why we resolve these?
I'll try. So I don't really do biology, but I do know that because we have this relationship between these small scale flows and bringing up nutrients, for example, from the ocean interior, then we tend to get a lot of fisheries that feed off of these currents. And if we are able to better understand these currents, better understand how they're changing, then we can also help support the communities as, for example, algae blooms come in and can affect crops, or how like fishing patterns might shift. So again, it's all part of that same story. In the Gulf of Mexico also, when there was the big oil spill, then a lot of the motivation of these small scales came because we didn't really understand where the oil was going and which coastlines it targeted in the end. And a lot of that was due to these small scales that were transporting the oil. So again, if we are able to better understand them, better model them, then we can help support more operational models. Yeah.
Yeah, and during Christoph's keynote talk earlier, he talked about energy sources and ways of expanding our renewable energy network, and he briefly touched on offshore wind farming, and I know that that's sort of been the discussion in Massachusetts. Do you expect that as we try to develop and scale up these offshore wind farms, that understanding the submesoscale will be important for that?
I actually don't know the answer to that. I do imagine it will affect the patterns to some extent. It will probably most likely affect how people access, for example, fisheries. Yeah. But I personally, I'm sorry, I don't have good intuition for how the submesoscales are affected by wind farms. Yeah. I think renewable energy is a good thing, and we should pursue it. I also know that people are looking at wave energy and how we can harness that. So that again depends on like the small scale mixing in the upper ocean, and I'm sure given the relationship with winds, I'm sure there's a relationship with wind farms as well.
For sure. Yeah. I guess pivoting to another part of your talk, you sort of showed at the beginning this really nice illustration of GCMs going from these really coarse, non-Rhode Island resolving models all the way to these order sub-mesoscale. And I guess, you've shown some really great work done using machine learning and convolutional neural nets and trying to understand and learn the physics. Do you suspect that I guess another train of thought is, well, maybe we should just work on brute force, increasing the resolution of our models, and that's that. Do you believe that that's sort of a feasible way forward that should happen as well? Or do we think that, that just because of the computational cost that we should really invest more into some of these machine learning methods?
Yeah, that's a really great question. It's actually a huge debate in the kind of modeling community as well, because one could argue that the resolution, high resolution will just kind of take away a lot of these problems. And the Oceananigans model that I mentioned is able to kind of reach very high resolution globally also, with the goal of removing a lot of these sensitivities to parameters. But I think there's only a certain degree we can go to, and even kind of their highest resolution model still will not resolve these small scales. Yeah. Will always be limited because you can't simulate a world within a world, right? And the resources we use for these simulations might outweigh kind of the benefit. We're using GPU-based stuff, or even CPUs. That's a huge carbon footprint, and there are some questions to be asked of how far do we want to push this further. There is some really cool work happening at MIT related to emulation. So rather than simulating all the processes in the model, the using certain emulation approaches to emulate the climate system. And then you are able to use real data, use high resolution models, but without having to run the full model. So those are some pretty cool opportunities to look out for. I think there's a lot of the climate ground challenge going on for that.
Yeah. Definitely an area of debate for sure. And so the convolutional, the neural networks that you were showing later that you sort of trained to do a really great job at understanding some of these processes. Could you give us a sense of how computationally expensive that was and sort of setting that up, and how flexible, do we think that can be applied to different ocean problems or atmosphere problems? Or is this sort of a big undertaking as it is in the current state?
Yeah, there's a lot of work to try to see how we can generalize also to different ocean fields also, and because there was a lot of very specific processing going on for this problem, I don't know if it could be generalized specifically, but the kind of the output, the prediction could certainly be adjusted in order to account for larger scale flows or smaller scale flows, and those are stuff that I'm working on right now to try to better understand.
Yeah, that's awesome. And so going back to sort of your PhD work, which is perhaps more theoretical, and you made some comparisons with the neural net, the true world, and then the theory. And then you sort of ended with, here are sort of the parameters and features that are most important. Has there been a development for you, at least, or even more generally, of bringing these knowings, these learnings back into the theory derived, and to sort of reduce the error for the theory driven parts of it?
Yeah, that's a really great question, especially because neural networks are really computationally expensive. So coding them up in a climate model is almost not worth it, because you could have millions or billions of parameters compared to a climate model, which is already kind of really extensive and heavy. So then if you add in a neural network, just one for one certain process, it's really a bit too much. So there is an effort to try to take what the neural network has learned, which has proven that there is, kind of this ideal solution that can be extracted from the data, and then go back to the theory and say, well, what is missing? What can we improve? And can we do that with just one parameter? So for example, we found that strain, which is related to this large scale flow, is really important for the network, but that's missing from the physics parameterization. So maybe there's a way that we can kind of theoretically write that up within one or two, kind of using just velocity, which is already solved by the model. So can we just use that in the climate model? So there is some work towards that. One could also apply an equation discovery approach, where you kind of set off to learn an equation from the data, and the neural network has learned, some relationship. So maybe that can be simplified to a certain equation. while accounting for kind of better data. So those are different directions.
For sure. And sort of from my background, which is perhaps more climate science, so maybe I'm not as familiar with neural networks, but my understanding at first glance is that like it may be sensitive to the kinds of input data you give, or perhaps how you tune in and things. How is that? So the multicolored dots that you showed, the different inputs that you gave, how were those chosen, and was there some sort of parameter testing for that as well to sort of really make sure that this was the best way to get it and not overfitting the data, I guess?
Yeah. So in order to choose kind of the right input features or the kind of input variables, that was based on like physical intuition. So I didn't really, there are infinite amount of variables you can choose, right? Because you can compute any physics from kind of the model outputs. So that was based on kind of intuition. And then the goal of kind of the last part of explaining what the neural network is doing is to kind of really back in and say, well, what's really important? And then kind of the next step potentially could be to remove everything that's not important and see how that works. I will say that kind of the goal of also applying it to real data from like I realized also when I came to MIT that when I say data, it's not what most people think of when I say data. So simulated data versus observational data is really that would give you the real world, right? And the simulation, there's a lot of highly correlated variables like temperature and velocity and stuff like that are all kind of co-calculated in a model, but in the real world, it is not. And if we're able to then extrapolate from the neural network onto real observational data, I think that will lead to a lot of really exciting discoveries because we can really get to, the bottom of what's really impacting these small scale turbulence.
Do you have, was there any thoughts or considerations for when you say simulate data, you showed us that one super high resolution model that you're taking as, real world almost. Mm-hmm. Was there and is there concern that may be improperly representing some of the features of or some of these relationships? Is that yeah?
Oh yeah. so the model only goes down to like 1 or 2 kilometers, whereas if we really wanted to get a lot of these small scale, we'd have to go down to several meters. So we know there's limitation in that approach. And again, yeah, I know, impossible. Yeah. But I'm currently experimenting with like a transfer learning approach, which is that we think that this kind of high resolution simulation captures some physics. And then if we can then go into real observations and kind of transfer the network, but then fine tune it on observations where we have less of, and it's maybe more sparse and noisy, then we'd be able to get like some sort of like real relationship between data and the physics. Yeah. But we'll see where it goes.
And as like sort of building off of the last panel, with the build environment, they talked about a big challenge as being how accessible some of this data may be and how difficult it may be to acquire. Sort of in your experience with gathering sort of the data for your sort of simulations and training, do you see data access as a potential friction or obstacle to sort of this in the oceanography field as a whole?
Yeah, absolutely. So that's kind of been a big challenge. And I think why the field has like entrained also a lot of people that are working on different angles of fluid dynamics. So people that are interested in simulations and building models and data-driven approaches because, well, it's also really hard to be an observational oceanographer. I've never been out to sea. I enjoy working from my couch at home, but some people actually go out for months at a time and take measurements. And then the end, your data set is, kind of a certain data set for a certain area for a certain time period. So we're definitely limited by the data that we can gather. And I really think that, since the Drifters program have started, which I think was about 10 years ago, we've had an exponential growth in available data, which only shows the potential for these type of like autonomous floating devices in order to give us the missing gaps.
Sure. I just want to be mindful of the time. Does anyone in the audience have any questions? Oh, Sean back there.
Yes. Oh, can you hear?
Yep.
Yes.
You're good.
Thanks for a great talk, actually. I've got a question. So what we're seeing in the ocean modeling world is we're seeing this emergence data-driven approach and going from kind of dynamics-driven approach to data-driven approach, slowly heading towards that direction with the emergence of ocean emulators slowly coming in place. And this is kind of analogous to what happened with the meteorology world, the numerical weather prediction world a few years ago, and people started working with the transition into some data-driven approaches, machine learning, weather models, and then suddenly, boom, all these corporations just came in. It's like, we have 3 different big models and make big pieces of news, and meteorologists were actually kind of furious about it because they're like, oh, these are things that were not consulted with forecasters and people don't know how to use them. And it's the corporates kind of coming in and kind of chipping into the academic world. And would you expect this kind of situation happening to the ocean modeling community? And what would you say for people to kind of come together before this happens?
Yeah, I think that's a really great question. So it's a very exciting time to kind of work in climate. And I think, the purpose of this workshop also shows the growing interest in the community. The ocean is still kind of like, space exploration in many ways. Like not a lot of people have successfully been to the bottom of the ocean, as we know. And it's quite dangerous. And we're trying to, sorry, that was bad. Hopefully we can remove that from the recording. We're trying to understand how we can get, further deep and get more measurements. And I can see the motivation. There's a lot of also work going on in carbon extraction, like from the ocean, and people are talking about geoengineering of how we can, sprinkle certain chemicals into certain parts of the ocean, how that will affect fishing economy, for example. And as there's more money involved and more governmental interest, then I think there are going to be more private companies that are coming in and trying to, it's not really taking advantage because there is a lot of work to be done also, but taking part, I say, in this exploration. I think it's a good thing. The question is, how can we make sure it's done responsibly? And also, how can we make sure that the data is available for everyone? Because if certain corporations build a climate model now, that's probably going to be better than, what we've been able to do for decades, because they have teams of people working on it, and they're so much more efficient than, the kind of timeline of academic papers coming out and people working in conferences is just different when it's in the industry. But, are they going to share the data with us and tell us like where climate is changing the most and where the ocean, where the sea level is going to rise? I think that could be a really good thing. It just needs to be open for everyone, and there needs to be collaboration with the experts in the field that have been thinking about this for a very long time. So hopefully that can happen.
Thank you. Here is Gwen Run from Leeds, and thank you for sharing all the insights, and it was really impressive. And my question is, how do you model the uncertainty in this model? Because as I understand, for climate model, reanalysis is important, but I think maybe we want to know more about future. We want to do prediction, and uncertainty is super important. If the uncertainty bound is really large, that means it may be meaningless to go really high, this kind of high precision. So I just want to know, how do you model uncertainty and how do you consider this kind of factors?
Yeah, that's a great question. So people have different approaches for this, but a lot of times people look at error compared to observations. So one can look at, for example, how your error propagates also over time, and is it bounded? And how does it compare if you run your model backwards? How does it compare to observations you've collected in the past? And also you could compare it to like certain metrics that are measurable, like for example, sea surface temperature, or the depth of the mixed layer in my work that you can get from these drifters in the locations that you have. So you can do these sort of like bounding approaches where you can compare with the data that you do have. But again, as you've seen the spread, despite our best efforts, we still have a lot of uncertainty moving into the future.
Ethan over there.
Thank you. Thanks for the great talk. I had two, I guess you've touched on it, I think at 2 points in the mentioning like using in situ measurements for transfer learning, and then also using it for model checking and error bounding. Are there other ways you see other main ways you see use of in situ data for models of this scale?
Yeah, people also use them for data assimilation. And there are some models that are actually are involved with data assimilation. So you have this kind of like pacing by the observations, and that's all generated by in situ measurements, surface measurements, and even like tide gauges kind of at the boundaries. And then when you have those as like initial conditions, you can run a model on top of that, and you can get like an estimate of the ocean. But those obviously can't be used for the future because you don't have data there. Yeah.
Cool. Yeah. Alan? Okay.
Are there regions of the ocean where like, you would really like to have this data to either validate your model or Are there regions of the ocean where you'd really like additional data to either improve your data-driven methods or just better validate your model?
Yes, probably the Southern Ocean is the current kind of place where a lot of people are trying to get data from, because the waves are extremely high and it's really hard to go out there. But also it's such a pacer on climate. So that's kind of true for the entire oceanography community, I think, and not me specifically. But there is a lot of data from the North Atlantic, for example, that I could potentially utilize already. But it's more of like, where are the places that are important for climate, like the Arctic, the Southern Ocean, maybe the equatorial Pacific, where we get like El Nino events. Those are all locations where you could get data in order to validate some of your problems. But at these small scales, even so, it's really tricky. So it's really hard for like the Southern Ocean. I don't know how you would get with the really high waves. You can't go there during winter because it's icy. And then you can't get, when you have the strongest mixing. So it's tricky.
Okay. So it's the environment is difficult, or is it also the resolution you're talking about?
It's both.
Limiting factor? Okay.
Yeah, it's both. Yeah. If like humans have to go out there, if we can figure out a way to do it, like with sea mammals, for example, that's, really cool. Or maybe like a robot that, mimics a sea mammal. But I think for for humans to gather stuff on a ship, it's really difficult to do things during winter conditions at the frequency that you would need it.
Cool. I want to finish with one last question. You briefly mentioned Climate Match Academy and something that you helped co-found. Do you want to, I guess, like briefly talk about like how that came to be, and so your inspiration, and maybe like, how that might be helping bridge the oceanographic and computational sciences communities?
Yeah, sure. I could talk about that for another hour, but I won't. So it kind of came about from my struggles to pre-process the data, which I mentioned briefly. But I came from a very theoretical background, and then my PhD I only just started to learn how to code towards the end of it. And then coming into this like data-driven approach in my postdoc, I had to learn a lot of tools. And that's when I realized that it's a huge barrier for people who don't know how to or haven't had the experience to work with, climate data. There's a lot of also specifics of climate data that I've learned are very different than other communities' problems. And a lot of that's related to how large our data sets get, and the fact that you need very long time series and very high resolution in space. And that just, gets massively huge. And the way kind of the data is saved and sliced, it's just, there's a lot that's involved in it. So there are a lot of tools that were developed. And there's a great like open source Python community also, and Julia now, that have worked on developing these tools. And the data, there's a lot of data that's open source. So the motivation really was, well, if we can teach people the tools and tell them where the data is, they can then go work on climate science from anywhere around the world. And then they can then think about problems that matter for their community locally, and then try to understand how climate is changing for them. And we got together, it was a bunch of people, actually most of them were from my PhD group in Brown. And we started thinking of what the tools are that people could use, and that really spiraled from there. We got people interested in like understanding crops and how their relationship to heat waves, and people. It wasn't just ocean, and how like the economy is changing based on sea level rise, and we had I think a few hundred people from around the world, almost 100 countries participate, which was really exciting, and they continued working on their projects later. A lot of people were from the global south, which as a climate science community, we're very limited in that type of diversity. So it's been really inspiring to be part of it, and mostly just see people being able to now start thinking about how climate is changing in their region and how they can like monitor it themselves.
Well, thank you so much. Let's give Abigail another round of applause.
Thanks, everyone.
Yeah.